Okay, so the final class for while I'm away is the volume of spheres and composite solids. And I mean, I don't know about you guys, but as soon as I saw that word, a little bit of fear entered my heart. But that's okay. Composite solids. Uh, Obviously, we've got to look at a situation much like composite uh, areas and surface area of composite solids. It requires a little bit more thought. We've got to start thinking in 3 dimensions. We've got to start thinking about what shapes make up our uh, our solid that we're trying to find the volume of in this case. But we'll start first with the spheres. Once again, there's a nice little formula for spheres, and this formula, I believe, is provided for you on your formula sheet. And we've just got to know when to use it. So it's important to understand these formulas in the sense that of recognizing when they get used. In this case, because a sphere only ever really has one dimension that we care about, which is the radius, there is no height of the object as well like a cylinder would have. The only dimension we're concerned with is the radius. We may not be given the radius, but that's the only dimension we're concerned with. So the fact that it says radius cubed, not radius squared, suggests we're going to be talking about a volume, not an area. So try and look at your formulas that way and try and get clues from the formulas. So in essence, it's almost, although we leave this to last, it's almost the simplest one for us to work out because we don't have to prove why a volume is calculated by using 4/3 of pi r cubed. We just have to know to use that one, and that means that the only item in this formula we're actually chasing is the radius. So really, we just have to watch any tricks that might be used to disguise from us the radius, or maybe we might have to think about half a sphere and understanding what that means. So for this first one, they've given us the radius there, so we can just simply grab the formula and start plugging in our values, and there is only one value to worry about. 4/3, well, that's just a number. Pi, that's just a number. All right, so the only thing we have to find out is what our radius is, and in this particular case, it's 4, and we need to cube 4. Very important that you cube 4, not square it, otherwise you will get the wrong response. So once again, we get to that point and we're just going to create a bit of calculation. So we've got 4/3 times pi times by 4. Now I'm just looking frantically at my calculator to find if there's a cube button. I know there's a cube root button. Yes, there is. So there's a cube button right there. Or if I didn't know that that cube button was there, I could use this Xbox button and I could put a 3 up there. Either way is fine. So we can either use this X cubed button here, or if we forget that that's there, like I just did at the start there, we can use what I call the Xbox button, and that'll create a little box up here and we can put a 3 in it. Either way, I'll get you the same answer. So we plug that through, and I'm going to round that one because it's so low. I'm going to round that just to the nearest whole centimetre. So we've got 268 centimetres cubed. And there we go. Okay, so for the second one, there's a slight little trick in there, and that is the diameter, not the radius. So we need to know we've got to halve that when we put that into our formula. So our formula for volume is 4/3 of pi r cubed. Whoop, that's a bit messy. We'll go back. Somehow I created a 3 with an extra loop on it. Not much better that time either. Oh, okay, so pen is being a little bit garbage with me. Just bear with me there and I'll fix my 3s up. All right, something's going wrong here. Hooray, we've got a 3. Look at that. That took a while. I'm sure that was interesting viewing for everybody here. Okay, so in this case, 4/3 times by pi, and our radius in this case is going to be 5. Half of what's given there is the diameter, and we've got to cube it. Okay, so let's plug that in the calculator. 4/3 times pi times 5 cubed. So what I can actually do here is I might just use this replay button because it's very similar to what I had before. I've just got to change that 4 to a 5, so I can use that replay button and work it out that way without having to write all that stuff into the calculator again. So I press equals, and I get 523.598. I might just round that to 523.6. So going back into the sheet here, 523.6. What are my units? Well, they're centimeters, and we're talking in 3 dimensions now, so we've got to say cubed. Okay, so the next question is determine the volume of this hemisphere. So a hemisphere is half of a sphere. So what we're going to need for this one is we're going to need that formula, that 4/3 of pi r cubed, but we're going to need to understand that we need to take half of that area. So I can just sort of take half of the whole lot there. I don't technically need the brackets there, but it just makes it a little bit easier to understand what it is I'm doing. So 4/3 times by pi, and the radius here is given, it's not a diameter, so that's just going to be that 12 centimeters, and I've got to cube that. So once again, I can just pick up my calculator and I can type that all in. So I need half times by 4/3 times by pi times by 12 cubed. I'll use that special button there instead of the different one that I used last time. And I just press equals, and that's going to give me my values. So because I halved it to start with, I don't have to worry about halving it now. That's the final answer. And I'm going to go to one decimal place and say 3619.1. And I'll look at my units, and they're in centimeters, so my answer will have to be in centimeters cubed. Okay, so for the next question, if the Earth was considered to be roughly spherical with a radius of 6,400 kilometers, what would the approximate volume of the Earth be? Well, if we're going to assume the Earth is a sphere, we just have to use the formula for the volume of a sphere. So 4/3 of pi r cubed. So once again, we can just add in that one value that we don't already have, and that is, they said radius, so I'm looking for the radius, so that's the right number. I don't have to worry about halving it. We're not talking about a diameter here. Now that's going to give me a rather large number, I suspect, but we'll plug that into the calculator and see what happens. So 4/3 times by pi times by 6,400 cubed. I might have said squared before, sorry if I did. Okay, so it's given me rather a large number there, but although it's larger than the screen would allow, it is, however, in scientific notation. So I could say, I could put it down just as my calculator has put it there, 1.0, sorry, I'm going to have to bring the calculator back so I can see it. I'll go 1.098. I think that's not a bad approximation. So 1.098 times by 10, and I think the power was 12, but I'll have another look at my calculator just to be sure. So that's right, yes, times 10 to the power of 12. So if I wanted to, I could maybe even write that out. So 1098, I've moved the decimal place 3 times, 1, 2, 3. I still need to add 9 more zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, and we're in kilometers, so that's kilometers cubed. Oh gosh, that's horrible. Apologies to people who like nice neat threes. There we go, that's better. Okay, and that number there is a 0, not a 6. It's a bit better. Okay, so that gives us our basic idea. Now, what's that? That's up to millions. That's billions. So 1,098 billion cubic kilometers. So yeah, quite a large number. Now, just moving on to composite solids. This is where we're looking at a situation where we might be adding or subtracting 2 or more solids. So here we've got, to get the volume of this particular object, I'm going to need to get the volume of that cylinder And I'm going to have to add to that the volume of the sphere. Okay, so the volume of the cylinder is just going to be that area of the base times the height. The area of the base of a cylinder is the area of a circle, so pi r squared h plus, and now volume of a sphere is 4/3 of pi r cubed. So as we substitute in there, our radius both of our sphere and of our hemisphere is 9 centimeters. And our height is 7, which is only really applicable to the cylinder, but not to the sphere, because the sphere sits on that 7 centimeter high cylinder. And once again, 4/3 pi, and our radius is 9, and we have to cube that. So we now just plug that into our calculator, and away we go here. Bit of clicking coming up. So pi times by 9 squared times by 7 plus 4/3 times by pi times by 9 cubed. Plug that through. So we are rounding to the first decimal point, 4834.9. And that is in centimeters cubed. And obviously I haven't been writing this enough. I'll put there that I've rounded that to 1 decimal place. Okay. Now this final question, I would like to point out, and I'm going to use a little highlighter here to point it out. The HSC papers go up to question 30, and this is from 2007, and you'll see it's question 30E. That's the last part of the last question of the HSC paper. So the people who wrote the paper tend to try and put questions in order of difficulty. This was considered the hardest question on that paper. So if it doesn't sit nicely with you, don't worry about that too much, because if it's the hardest question on a General 2 paper, it's unlikely to be on a Standard 1 paper. I may run out of time, so what I'm going to do first is just go with the basic idea of how we're going to solve it. Now, a very important thing, like always, I'd be looking at some key terms in here, and it says a solid is made up of a sphere sitting inside a cone, right? And then it gives me some information. And what I really do notice is they keep referring to this solid as a solid. The solid has a total height of this. The solid and its cross-section are shown, but they don't ask for the volume of the solid. They say, what's the volume of the cone? Okay, so we don't need to know the volume of this whole object. We're interested in the volume of this part down here, okay, which is considerably easier, but still quite a job. Now, the first thing we're going to have to realize is we need to know the radius of this base of the cone, and we don't have that information. What we have is the radius of this sphere, and we know that the recess is in 2 centimeters. So what we've actually got to do is we've got to, and this is a big jump, we've got to think, well, we need to know this distance. We need to know this distance here. And once we know this distance here, we can get this distance here, which would be the radius of the base of our cone. So if we know that that's 4 centimeters there, the radius would also be 4 centimeters here, less that 2 centimeters. So, well, that's 2 centimeters there. And we can use Pythagoras. I am going to run out of time, so I'll just go quickly. I won't give the full response. So we can use Pythagoras, therefore, to find out this distance. So 4 squared minus 2 squared, so that's 16 minus 4. So this is going to be the square root of 12 is going to be this distance here. And then it is just simply the case of finding the area of the cone with a radius of the square root of 12. You could put that in your calculator and get that to certain decimal places. And then we've also got to realize that this height is of the whole thing. We only want to know the height of the cone. So that would be that whole 15 minus the 4 centimeter radius minus this 2 centimeters here, so minus 6 centimeters, which would be 9 centimeters tall. And then we just find the area of the cone, 9 centimeters tall, the radius of root 12. And with that, I have 10 seconds left in this video. If you want a longer explanation of this, ask me on Friday. Thanks.